Space is weird. Like, genuinely, deeply, fundamentally weird. And the more we look at it, the weirder it gets. Every time astronomers point a new telescope at the sky, they find something that makes them go, wait, that shouldn't exist. And today, we're talking about 10 of those things. 10 structures so massive, so bizarre, and so utterly confusing that the smartest people on Earth are basically just shrugging their shoulders and saying, we have no idea. Before we dive in, do me a favor. Drop a comment telling me where you're watching from and what time it is where you are. I'm genuinely curious how far this video travels. Are you watching at 3 a.m. because you can't sleep? Are you on your lunch break? Are you watching this on a bus, on a train, at work, when you should be doing something else? Let me know. It's always wild to see people from opposite sides of the planet watching the same video at the same time. We're all just tiny specks on a rock floating through space, looking up at the same stars. Anyway, let's talk about those stars and the absolutely insane things hiding between them. I should warn you up front. What we're about to discuss is going to mess with your sense of scale. You think you understand big. You don't. None of us do. Our brains evolved to understand things like trees and mountains and maybe the distance to the next village. We did not evolve to comprehend billions of light years. So when I throw numbers at you, just know that I'm not exaggerating. If anything, I'm underselling it. The universe is genuinely that absurd. So here's the thing about the universe. It's supposed to follow rules. Gravity pulls things together. Light travels at a certain speed. Matter clumps up in predictable ways. These are the rules. Scientists have spent centuries figuring them out, testing them, proving them over and over again. And then the universe just goes ahead and breaks its own rules. Because apparently, the cosmos doesn't care about our textbooks. The structures we're about to discuss aren't just big. They're incomprehensibly big. Your brain literally cannot process how large these things are. When I say something is 1 billion light years across, that's just a number to you. It doesn't mean anything real. Because 1 billion light years is so far beyond human experience that our brains just kind of shut down and go, okay, sure, big number, whatever. But these structures exist. We've photographed them. We've measured them. And we still don't understand how they got there. Let's start with something that shouldn't be possible according to everything we know about physics. The first structure is called the Hercules-Corona Borealis Great Wall. And yes, that name is a mouthful. But trust me, the name is the least crazy thing about it. This thing is the largest known structure in the observable universe. When I say largest, I need you to understand what that means. This structure is approximately 10 billion light years across. The observable universe itself is only about 93 billion light years in diameter. So this single structure takes up more than 10% of everything we can see. Let me put that in perspective another way. Light, which is the fastest thing in the universe, would take 10 billion years to cross from one side of this structure to the other. 10 billion years. The Earth is only about 4.5 billion years old. So if light started traveling across this structure when Earth was first forming, it still wouldn't be halfway across yet. That's insane. Here's another way to think about it. The Milky Way galaxy, our home, is about 100,000 light years across. That already feels impossibly huge. The Hercules-Corona Borealis Great Wall is 100,000 times bigger than our entire galaxy. If our galaxy were the size of a marble, this structure would be about 600 miles long. You could fit millions and millions and millions of galaxies inside this thing. But here's the problem. According to our current understanding of physics, This structure shouldn't exist. The universe is only about 13.8 billion years old. That means there hasn't been enough time for something this big to form through normal gravitational processes. Gravity works by pulling matter together slowly over time. Galaxies form, then clusters of galaxies form, then superclusters. It's a gradual process. But for something 10 billion light-years across to exist, gravity would have needed way more time than the universe has been around. Think about it this way. After the Big Bang, matter was spread pretty evenly throughout the universe. It was like a thin cosmic soup with tiny variations in density. Over time, gravity pulled the slightly denser regions together. Those regions grew, attracting more matter, eventually forming the first stars and galaxies. This process takes time, a lot of time. And even after billions of years of gravitational clumping, the largest structures should only be about 1.2 billion light-years across, according to our best models. The Hercules-Corona Borealis Great Wall is almost 10 times bigger than that limit. Scientists discovered this structure in 2013 when they were mapping gamma-ray bursts. Gamma-ray bursts are these incredibly powerful explosions that happen when massive stars die or when neutron stars collide. They're so bright that we can see them from billions of light-years away. In fact, a single gamma-ray burst can briefly outshine entire galaxies. They release more energy in a few seconds than our sun will release in its entire lifetime. And when astronomers plotted out where these bursts were coming from, they noticed something weird. There was a region of space where there were way more gamma-ray bursts than there should have been. Way more. Now, gamma-ray bursts are supposed to be pretty evenly distributed across the sky. The universe, on large scales, is supposed to be homogeneous. That's one of the fundamental principles of cosmology. It means that if you zoom out far enough, every part of the universe should look pretty much like every other part. There shouldn't be giant clumps or empty spots. It should be relatively uniform. This principle is called the cosmological principle, and it's the foundation of modern cosmology. Without it, we can't make any predictions about the universe at all. The Hercules-Corona Borealis Great Wall violates this principle in a big way. It represents a massive concentration of matter that shouldn't have been able to form given the age of the universe. Some scientists have suggested that maybe it's not a single structure, but several separate structures that just happen to line up from our perspective. Others have proposed that our models of structure formation might be incomplete, but no one has a satisfying answer for how this thing exists. The researchers who discovered it, a team including István Horváth, at the National University of Public Service in Hungary, were shocked by their own findings. They triple-checked their data. They ran statistical tests to see if it could be a fluke. It wasn't. The structure was really there, and it really was that big. They published their findings, and the scientific community has been scratching its head ever since. And this brings us to our second structure, which is almost equally confusing, but in a completely different way. The Boötes Void is basically the opposite of the Hercules-Corona Borealis Great Wall. Instead of being a giant concentration of matter, it's a giant concentration of nothing. This is a region of space approximately 330 million light-years in diameter that contains almost no galaxies. Almost none. In a region of space that big, you would expect to find around 2,000 galaxies. The Boötes Void contains about 60. That's it. 60 galaxies in a space that should have 2,000. To really appreciate how strange this is, you need to understand the normal distribution of galaxies. In most parts of the universe, galaxies are pretty common. They clustered together in groups and clusters, connected by filaments of dark matter and gas. This creates a cosmic web structure, like a giant three-dimensional spider web made of galaxies. The voids between the filaments are relatively empty, but they still contain some galaxies. Not the Boötes Void. The Boötes Void is like someone took a cosmic cookie cutter and just removed everything. Think about how empty that is. If our Milky Way galaxy were located in the center of the Boötes Void, we wouldn't have discovered that other galaxies existed until the 1960s. The nearest galaxy would have been so far away that with older telescopes, we simply wouldn't have been able to see it. We would have thought our galaxy was the entire universe. We would have been completely alone, looking up at a sky filled with nothing but the stars in our own galaxy, with no idea that trillions of other galaxies existed beyond our view. Imagine the philosophical implications of that. For most of human history, we thought the stars in our sky were the entirety of the cosmos. Then we discovered that many of those fuzzy patches were actually entire galaxies, each containing billions of stars. Our universe got much, much bigger. But if we had evolved in the Boötes Void, that revelation would have come much, much later. We might still think we were alone, still think our galaxy was everything. The Boötes Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the distribution of galaxies in a section of the sky and found this enormous empty region. At first, they thought it was a mistake. They thought maybe their equipment was malfunctioning or they were looking at data wrong. But the more they looked, the more they confirmed that this void was real, and it was massive. Kirshner described his reaction to finding it as a mix of excitement and confusion. Here was this enormous feature that no one had predicted, no one had expected, and no one could immediately explain. It was like finding a giant hole in the ocean where the water just stopped. It shouldn't be there, but it was. So how does something like this form? Honestly, we're not entirely sure. One theory is that the Boötes Void is the result of several smaller voids that merged together over billions of years. As the universe expanded and matter clumped together into filaments and walls of galaxies, these empty spaces between them could have merged into one giant supervoid. But the simulations don't quite match up. When scientists run computer models of how the universe should have evolved, they don't produce voids this big. They produce smaller voids, and they produce lots of them, but not single supervoids of this magnitude. Another theory is that the Boötes Void is actually growing. As the universe expands, dark energy pushes galaxies apart, and voids get bigger over time. The Boötes Void might have started out as a normal-sized empty region and just kept growing. But even this doesn't fully explain why it's so incredibly empty compared to surrounding regions. Other voids are growing too, but they still have more galaxies than the Boötes Void. Some people have jokingly suggested that maybe an advanced alien civilization cleared out the void as living space. This is obviously not a serious scientific theory, but it speaks to how bizarre and unexplainable this structure is that people even consider ideas like that. When your best explanations are maybe our physics is wrong or maybe aliens did it, you know you've found something genuinely mysterious. The few galaxies that do exist in the Boötes Void are interesting in their own right. They're arranged in a tube-like pattern through the center of the void, suggesting that they might be connected to filaments at the edges. Some scientists think these galaxies might be relatively recent arrivals, having drifted into the void from its eddies over time. Others think they might be the remnants of whatever process emptied out the void in the first place. Either way, they're lonely. The nearest neighbor for a galaxy in the Boötes Void is typically tens of millions of light years away. That's a lot of empty space. The third structure on our list is the giant GRB ring. And this one is particularly weird because it might not even be a physical structure at all. Let me explain. In 2015, astronomers discovered what appeared to be a ring of galaxies in the distant universe. This ring is about 5 billion light-years in diameter. That's massive. To put that in perspective, the distance from Earth to the most distant galaxies we can see is about 13 billion light-years. So this ring spans a significant fraction of the observable universe. The ring was identified by looking at the distribution of gamma-ray bursts, similar to how the Hercules-Corona Borealis Great Wall was found. When scientists mapped out these bursts, they noticed that 9 of them formed what looked like a ring shape in the sky. Gamma-ray bursts, remember, are these incredibly powerful explosions that mark the deaths of massive stars or the collisions of neutron stars. They happen at random times in random places, and they're visible from billions of light years away. Scientists have detected thousands of them over the years, and normally they're spread pretty evenly across the sky. Finding 9 of them arranged in a ring pattern is strange. Very strange. Now here's where it gets complicated. The gamma-ray bursts in this ring all occurred between about 5 and 7 billion light-years from Earth, and they appear to form a ring. That's about 1/6 the diameter of the observable universe. If this is a real physical structure, it would be one of the largest things ever discovered. It would also be completely impossible according to our current understanding of how the universe works. The cosmological principle says that the universe should be the same in all directions on large scale. There shouldn't be giant rings or walls or specific shapes. The maximum size for any structure, according to current theory, should be about 1.2 billion light-years. The giant GRB ring is more than 4 times larger than that limit. It simply shouldn't exist. The discoverers of the ring, led by Lajos Balázs at Konkoly Observatory in Hungary, were cautious in their announcement. They knew how extraordinary the claim was. They also knew that extraordinary claims require extraordinary evidence, and they weren't entirely sure they had it. The main question was whether the ring was a real structure or just a statistical fluke. But here's the thing. It might not actually be a ring. It might just look like a ring from our particular position in space. We're seeing these gamma-ray bursts from one specific viewpoint, and they might just happen to line up in a way that looks like a ring to us, even though they're not actually connected in any physical way. This is called a projection effect, and it happens a lot in astronomy. Think about constellations. The stars in Orion look like they form the shape of a hunter from Earth. But those stars are actually at completely different distances from us. They're not physically connected. They just look connected from where we're standing. Betelgeuse, the star that forms Orion's shoulder, is about 700 light-years away. Rigel, the star at his foot, is about 860 light-years away. They're not close to each other at all. They just happen to be in roughly the same direction from our viewpoint. The giant GRB ring might be the same kind of illusion. The gamma-ray bursts might be at different distances, in galaxies that have nothing to do with each other, and they just happen to form a ring shape from Earth's perspective. This is a perfectly reasonable explanation, and many astronomers think it's the most likely one. Scientists are still studying this one, and there's genuine debate about whether it's real or just an optical coincidence. More data is needed. More gamma-ray bursts need to be detected and mapped. Until then, the giant GRB ring remains one of the most tantalizing mysteries in modern astronomy. The fourth structure is called the Huge Large Quasar Group. Yes, that's really its name. Huge LQG for short. And it's another one of those things that makes physicists uncomfortable. They're among the brightest things in the entire universe, and understanding what they are helps you appreciate why finding a group of them is so significant. A quasar is basically the core of a galaxy where a supermassive black hole is actively feeding on surrounding matter. When gas and dust fall toward a black hole, they don't just disappear quietly. They form a swirling disk around the black hole, heating up to millions of degrees through friction. This disk emits enormous amounts of radiation, enough to outshine the entire galaxy around it. A single quasar can be hundreds of times brighter than a galaxy containing 100 billion stars. Because they're so bright, we can see quasars from incredibly far away. Some quasars we've detected are over 13 billion light-years from Earth, meaning we're seeing them as they were just a few 100 million years after the Big Bang. They're like cosmic lighthouses, marking the locations of the most massive black holes in the early universe. In 2013, scientists discovered that 73 quasars were grouped together in a way that formed a massive structure about 4 billion light-years across. That's more than 3 times larger than the supposed theoretical limit for cosmic structures. The quasars in this group are not just randomly scattered. They appear to be organized in a way that suggests they're part of something bigger, something connected. The huge LQG was discovered by Roger Cloutz and his team at the University of Central Lancashire. They were mapping quasars and noticed this unusual clustering. When they analyzed the data, they found that these 73 quasars were forming a structure that shouldn't be possible. Not according to current physics, anyway. He was one of the scientists who found the Klaus-Campusano Large Quasar Group back in 1991, which we'll talk about later. So he knew what he was looking at when the huge JLQG showed up in his data. And he knew it was trouble for the standard model of cosmology. What makes this even weirder is that the huge JLQG is not the only large quasar group out there. There are others, and they all seem to be bigger than theory says they should be. It's like the universe is telling us that our rule about the maximum size of structures is just plain wrong. But if that rule is wrong, then what else might be wrong about our understanding of how the universe works? The cosmological principle is supposed to apply everywhere. If it doesn't, we're in uncharted territory. All our models of cosmic evolution, all our predictions about the fate of the universe, depend on the assumption that the universe is roughly the same everywhere. If there are regions that are fundamentally different, then all bets are off. Some scientists have argued that the huge LQG isn't really a single structure, but multiple structures that overlap from our perspective. They say that if you look at it carefully, you can break it up into smaller pieces that individually fit within the theoretical limits, but others disagree. They say the statistical analysis clearly shows it's a coherent structure, not just a random collection of quasars. This debate is ongoing, and that's kind of the point. When it comes to these cosmic megastructures, we often don't have clear answers. We have observations that challenge our theories, and we have scientists arguing about what those observations mean. That's how science works. But it also means that some of the biggest things in the universe remain genuine mysteries. The fifth structure is the cold spot in the cosmic microwave background. This one is different from the others because it's not a collection of galaxies or quasars. It's literally a cold spot in the leftover radiation from the Big Bang. and it might be evidence of something truly extraordinary. Okay, let me back up and explain. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the universe cooled down enough for atoms to form and for light to travel freely through space. Before that moment, the universe was so hot and dense that light couldn't travel anywhere. Photons would just bounce off free electrons before they could get very far. Suddenly, photons had nothing to bounce off of. They could travel freely, and they've been traveling ever since, filling the entire universe with ancient light. When we look at the CMB, we're literally seeing the moment the universe became transparent. It's the baby picture of the cosmos. This light has been traveling for over 13 billion years, and as the universe has expanded, it has stretched. What was once visible light is now microwave radiation. It fills all of space, coming from every direction equally, and it's incredibly uniform. If you measure its temperature across the entire sky, it varies by only about 1 part in 100,000. That's ridiculously smooth. It's like a perfectly flat surface with only the tiniest bumps and dips. These tiny variations are what eventually grew into the galaxies and clusters we see today. Gravity pulled matter toward the slightly denser regions, amplifying those tiny differences over billions of years until they became the cosmic web of galaxies we observe. But the variations in the CMB are incredibly small. We're talking about temperature differences of millionths of a degree. The technology required to measure such small differences didn't exist until relatively recently. When scientists finally mapped the CMB in detail, they expected to see a nearly uniform glow with tiny random fluctuations, and that's mostly what they found. Except for one spot. In the southern sky, there's a region of the CMB that's significantly colder than the rest. Not by a lot in absolute terms, but by a lot compared to how uniform everything else is. This cold spot is about 70 microkelvins cooler than the average CMB temperature, and it spans about 10 degrees of the sky. That doesn't sound like much, but in the context of the CMB, it's enormous. It's like finding a valley in what should be a perfectly flat plain. The cold spot was first noticed in 2004 when scientists were analyzing data from the WMAP satellite, one of the first missions to map the CMB in high detail. At first, people thought it might be a statistical fluke. When you're looking at something as vast as the entire sky, you're bound to find some regions that are slightly warmer or cooler just by random chance. The odds of finding any particular feature might be low, but the odds of finding some unusual feature somewhere are pretty high. But as more data came in, the cold spot remained. It wasn't going away, and it became harder to explain as just a random fluctuation. The Planck satellite, which launched in 2009 and produced even more detailed maps of the CMB, confirmed that the cold spot was real and not an artifact of the earlier measurements. Something was actually making that region of the early universe colder than itself. One popular theory is that the cold spot is caused by a supervoid, a giant empty region of space like the Boötes Void but even larger. When CMB light passes through a void, it can lose energy due to an effect called the integrated Sachs-Wolf effect. Here's how it works. The light falls into the void and gains energy, like rolling down a hill. But as it climbs out the other side, the universe has expanded, and the void is shallower than it was. So the light loses more energy climbing out than it gained falling in. This makes the light redder which translates to colder temperatures in the CMB. In 2007, astronomers found evidence for a supervoid in the direction of the cold spot. It's estimated to be about 1.8 billion light-years across, making it one of the largest known structures in the universe. This seemed like a smoking gun. The supervoid could explain the cold spot, but here's the problem. When scientists calculated how much this supervoid should affect the CMB, they found it couldn't fully explain the cold spot. The supervoid could account for maybe 20 to 30% of the temperature dip. The rest remains unexplained. Something else must be contributing to the coldness, but we don't know what. Some more exotic theories have been proposed. One suggestion is that the cold spot could be evidence of a collision between our universe and another universe in a multiverse scenario. If our universe is just one bubble in an infinite sea of bubble universes, then occasionally those bubbles might touch. When two universe bubbles touch, the thinking goes, it could leave an imprint on the CMB that looks like a cold spot. This is highly speculative and definitely not mainstream physics, but the fact that scientists are even considering it shows how puzzling this feature is. Other researchers have proposed that the cold spot might be a result of unusual physics in the early universe, like a cosmic texture or a primordial bubble from a phase transition. These ideas get pretty technical, but the basic concept is that something weird might have happened in the first moments after the Big Bang that left a mark on the universe. A mark we can still see today in the CMB, but none of these explanations have been confirmed. The cold spot remains one of the strangest features in the CMB, and we still don't fully understand what caused it. It might turn out to have a mundane explanation. It might just be an unusually large, random fluctuation that we're overinterpreting, or it might be a window into physics we don't yet understand. Either way, it's a reminder that even the oldest light in the universe still holds mysteries. The sixth structure is the Klaus-Campusano Large Quasar Group. This is actually the structure that led to the discovery of the huge LQG we talked about earlier. It was discovered in 1991 by Roger Klaus and Luis Campusano, and at the time, it was the largest known structure in the universe. The Klaus-Campusano LQG contains 34 quasars spread across a region about 2 billion light-years in size. That might not sound as impressive as some of the other structures we've discussed, but remember, in 1991, this was groundbreaking. No one had ever found a structure this large. It challenged the cosmological principle and sparked a lot of debate about whether such large structures could really exist. What makes the Klaus-Campusano LQG particularly interesting is its shape. The quasars aren't randomly distributed. They seem to form a coherent shape, almost like a filament or a wall. This suggests that they're connected in some way, that they're part of a larger cosmic web structure that we're only seeing a piece of. The discovery of this structure was a wake-up call for cosmologists. It showed that the universe might be less uniform than we thought, and it set the stage for the discovery of even larger structures in the years that followed. Without the Klaus-Campusano LQG, we might not have gone looking for things like the huge LQG or the Hercules-Corona Borealis Great Wall. But the fundamental mystery remains the same. How did these quasars end up grouped together? Quasars are thought to be active galaxy centers, and the galaxies that host them should have formed through the gradual gravitational accumulation of matter. For 34 of them to end up in such a concentrated region suggests that there's something special about that part of space. Some underlying structure or density enhancement that drew matter together. But what that underlying structure is and how it formed so quickly remains unclear. The seventh structure is something called the Laniakea supercluster. Now, this one is special because it includes us. We're part of it. The Milky Way galaxy, our home, is located within the Laniakea supercluster. So this isn't just an abstract cosmic curiosity. This is our cosmic neighborhood, our place in the universe. Laniakea was identified in 2014 by a team led by Brent Tully at the University of Hawaii. The name comes from Hawaiian and means immense heaven, which is pretty appropriate given how big this thing is. Laniakea contains about 100,000 galaxies spread across a region roughly 520 million light-years in diameter. That includes our own local group of galaxies, the Virgo supercluster, and many other smaller groups and clusters. To understand our place in Laniakea, you need to zoom out step by step. The Milky Way is part of a small collection of galaxies called the local group, which includes our nearest large neighbor, the Andromeda Galaxy, plus a few dozen smaller galaxies. The local group is about 10 million light-years across. That already feels huge. But the local group is itself just a tiny part of the Virgo supercluster. A larger collection of galaxy groups and clusters centered on the Virgo cluster, about 50 million light-years away. The Virgo supercluster was, for many years, thought to be the largest structure we were part of. But it turns out even the Virgo supercluster is just a small lobe of something much, much bigger. That something is Laniakea. What makes Laniakea interesting from a scientific perspective is how it was discovered. The team didn't just look at where galaxies are located. They looked at how galaxies are moving. See, gravity causes matter to flow toward denser regions. Galaxies aren't just sitting still. They're constantly being pulled toward the centers of mass around them. It's like water flowing downhill. Galaxies flow toward the gravitational valleys in the cosmic landscape. By mapping these movements, scientists can identify the gravitational basins that galaxies are falling into. This is like mapping the watershed of a river by tracking which way water flows. If water in one area flows toward a particular river, that area is part of that river's watershed. Similarly, if galaxies in one region of space are all flowing toward a particular point, that region is part of that point's gravitational basin. Laniakea represents one such basin. All the galaxies within it are flowing toward a region called the Great Attractor. The Great Attractor itself is another cosmic mystery. It's a gravitational anomaly located about 250 million light-years away in the direction of the Centaurus and Hydra constellations. Something is pulling our galaxy and millions of others toward it, but we can't see what it is because it's located behind the plane of our own galaxy, obscured by all the dust and stars in the way. When you look toward the center of the Milky Way, you're looking through the thickest part of our galaxy's disk. There are so many stars and so much dust in the way that visible light from beyond can't get through. It's called the zone of avoidance because astronomers have to avoid that part of the sky when trying to study distant galaxies. The Great Attractor is hiding there, pulling on us, but invisible to our telescopes. And we now know that it's associated with a large concentration of matter, including the Norma cluster, a massive galaxy cluster. But even accounting for all the matter we can see, there seems to be more gravitational pull than expected. Some scientists think there might be additional mass hidden from view, possibly more galaxy clusters that we haven't detected yet. But here's what's puzzling about lightyears. It's not gravitationally bound. Unlike smaller structures like galaxy clusters, which are held together by gravity, lightyears is too big to resist the expansion of the universe. The galaxies within it are being pulled toward the great Attractor. But at the same time, the universe is expanding, stretching space itself and pulling those galaxies apart. Eventually, lightyears will dissipate. The galaxies on its edges will drift away, carried by the expansion of space. So lightyears is a transient structure. It exists now, but it won't exist forever. Billions of years from now, the cosmic web will have stretched and shifted, and the gravitational basin we call lightyears will have changed beyond recognition. New structures will form, old ones will dissolve. And this raises interesting questions about how we define structures in the first place. Is something really a structure if it's not going to stay together? Scientists debate this. Some argue that lightyears shouldn't be counted as a structure at all because it's not bound. Others argue that it clearly represents a meaningful pattern in how matter is distributed, even if it's temporary. After all, a river is a real thing, even though the water in it is constantly changing. The eighth structure is the giant arc. This one was discovered very recently, in 2021, and it immediately caused a stir in the astronomical community. It also happens to be in the same region of sky as several other massive structures, which has led to some interesting speculation. The giant arc is a crescent-shaped arrangement of galaxy clusters, and gas that spans about 3.3 billion light-years of space. If you could see it in the night sky, it would cover the width of about 20 full moons. But of course, you can't see it with the naked eye, because it's incredibly far away. About 9.2 billion light-years from Earth. We're seeing it as it was 9.2 billion years ago, when the universe was less than half its current age. Alexia Lopez, a doctoral student at the University of Central Lancashire, discovered the giant arc while studying the light from distant quasars. Her work built on techniques developed over decades for mapping the distribution of matter in the universe. When light from a quasar passes through a cloud of magnesium gas, it leaves a signature absorption line in the spectrum. By looking for these signatures, astronomers can map where the gas is located between us and the quasar. Lopez was analyzing data from the Sloan Digital Sky Survey, a massive project that has mapped millions of celestial objects. She found that the magnesium absorption wasn't randomly distributed. It formed a coherent arc structure that was, frankly, way too big to exist. According to conventional physics, remember that theoretical limit we keep talking about, the 1.2 billion light-years maximum size for cosmic structures. The giant arc is almost 3 times larger than that. Or there's something about structure formation that we fundamentally don't understand. Lopez presented her findings at the 238th meeting of the American Astronomical Society, and the response was, to put it mildly, skeptical but intrigued. Some astronomers pointed out that the human brain is very good at finding patterns, even where none exist. We see faces in clouds and constellations in random stars. Our pattern recognition systems evolve to find threats and opportunities in our environment, and they're a bit too eager sometimes. Maybe the giant arc is just an illusion, a coincidental arrangement that looks like an arc from our perspective, but isn't actually a connected structure. But Lopez and her colleagues did statistical analysis to check for this. They found that the probability of such an arrangement occurring by random chance was very low. They ran simulations, generating random distributions of matter. The arc appears to be a real feature, not just a trick of perspective. What makes this even more interesting is that the giant arc is located in the same part of the sky as the huge QG and the Claus Compusano LQG. All of these massive structures are in roughly the same direction from Earth. Is that a coincidence? No one knows for sure, but it's definitely suspicious. Either we're incredibly lucky to have found 3 impossible structures in the same direction, or something about that direction is fundamentally different from the rest of the universe. Some scientists have proposed that there might be a common cause. Some feature of the early universe that affected that entire region of space and led to the formation of multiple oversized structures. But this is speculative. The giant arc, like so many of the structures on this list, remains an open question. The 9th structure is the South Pole Wall. This one was discovered in 2020, and it's literally right behind our own galaxy, hidden from view until advanced mapping techniques revealed it. This discovery was humbling because it showed us that even in our cosmic backyard, there are enormous things we've been missing. The South Pole Wall is a wall of galaxies stretching about 1.4 billion light-years across. It contains hundreds of thousands of galaxies and is located about 500 million light-years from Earth. In cosmic terms, that's practically next door. The nearest large galaxy to us, Andromeda, is only about 2.5 million light-years away. The South Pole Wall is 200 times farther than that, but still close enough that we really should have noticed it sooner. So why didn't we? The answer lies in our position in space. Despite being relatively close by cosmic standards, we didn't discover the South Pole Wall until recently because it's located in the zone of avoidance, the region of the sky that's obscured by the disk of our own Milky Way galaxy. The zone of avoidance is frustrating for astronomers. When we look toward the center of our galaxy, we're looking through billions of stars, dust, clouds, and interstellar gas. All that stuff blocks our view of what's behind it. It's like trying to look through a thick fog. You can see some things, but a lot is hidden. Light from distant galaxies gets absorbed and scattered by the dust in our galaxy's disk, making it impossible to see what's on the other side. For most of the history of astronomy, the zone of avoidance was simply a blank spot on our maps. We knew stuff was probably there, but we couldn't see it, so we couldn't study it. Different wavelengths of light can penetrate the dust better than others. Radio waves and infrared light can get through more easily, but optical telescopes are largely blind in that direction. The South Pole Wall was discovered using a technique called the cosmic flow surveys, which map the velocities of galaxies rather than just their positions. By seeing how fast galaxies are moving and in what direction, scientists can infer what gravitational structures must be pulling on them, even if those structures are hidden from direct view. It's like detecting a planet around a distant star by watching how the star wobbles. You can't see the planet directly, but you can see its gravitational influence. The team that discovered the South Pole Wall, led by Daniel Pomered at Paris-Seckley University and Brent Tully at the University of Hawaii, the same researcher who discovered Laniakea, used data from thousands of galaxies to map the flow of matter in our cosmic neighborhood. And there it was, a massive wall of galaxies curving around behind our galaxy, invisible to direct observation, but unmistakable in the gravitational data. What's remarkable about the South Pole Wall is how close it is, and yet how recently we found it. This is a genuinely enormous structure, comparable in size to the Sloan Great Wall, which was previously considered one of the largest known structures, and it was right there, hiding behind our galaxy the whole time. It's like discovering a mountain range in your backyard that you never noticed because a fence was in the way. The South Pole Wall does fall within the theoretical size limit for cosmic structures, unlike some of the other things on this list. So it doesn't necessarily challenge physics in the same way that the Hercules-Corona Borealis Great Wall does. But its discovery raised important questions about what else might be hiding in the zone of avoidance. How many other massive structures are we missing because our own galaxy is in the way? Scientists estimate that about 20% of the sky is significantly obscured by the Milky Way. That's a lot of hidden universe. The South Pole Wall might just be the first of many large structures waiting to be discovered in that blind spot. As our techniques improve and we develop better ways to see through the galactic dust, who knows what else we'll find lurking behind the curtain. And now we come to the 10th and final structure on our list. This one is perhaps the most famous, and definitely the most controversial. It's called Tabby's Star. And yes, I know it's a star and not a mere structure. But the reason it's on this list is because of what might be around it. Tabby's Star, officially known as KIC 8,462,852, is a star located about 1,500 light-years from Earth in the constellation Cygnus. It was observed by the Kepler Space Telescope, which was designed to find exoplanets by watching for tiny dips in starlight when planets pass in front of their stars. Kepler found thousands of planets this way, and it also found Tabby's Star. What makes Tabby's Star unusual is the way its light dims. Normal planet transits cause the star's light to dip by about 1% or less, and they happen at regular intervals. Tabby's Star dims by up to 22%, and the dimming events are irregular and unpredictable. Sometimes they last for days. Sometimes the star dims just a little, and sometimes it dims dramatically. There's no pattern that anyone can identify. The star is named after Tabitha Boyajian, the astronomer who first brought attention to its strange behavior. In 2015, she and her team published a paper outlining the observations and listing possible explanations. They considered things like a swarm of comets passing in front of the star, a cloud of dust from a planetary collision, or even instrumental errors. None of these explanations fit perfectly. And then someone suggested something wild. What if the dimming was caused by an alien megastructure? The idea of a Dyson sphere, or Dyson swarm, has been around since the 1960s. Freeman Dyson proposed that an advanced civilization might build a structure around their star to capture its energy. Such a structure would cause irregular dimming patterns as it moved across the face of the star. And the dimming pattern of Tabby's Star looked kind of like what you might expect from an incomplete Dyson swarm. To be clear, most astronomers don't actually think there's an alien megastructure around Tabby's Star. The scientific consensus is that the dimming is probably caused by dust, possibly from a recently destroyed moon or a swarm of comet fragments. Observations with other telescopes have shown that the light dims more at some wavelengths than others, which is consistent with dust but not with a solid object like a megastructure. But here's why it's still on this list. We still don't have a definitive explanation. The dust hypothesis has problems too. Where did all that dust come from? Why is there so much of it? Why doesn't the star show the infrared excess that you'd expect if it were surrounded by dust? The questions keep piling up and the answers remain elusive. Tabby's star represents a different kind of cosmic mystery. It's not that we've found a structure that's too big. It's that we've found a phenomenon that doesn't fit neatly into any of our categories. It might be entirely natural, something we'll understand once we gather more data. Or it might be something genuinely unprecedented, something that forces us to expand our understanding of what's possible in the universe. And that, really, is the thread that connects all 10 of these structures. They all challenge us. They all force us to ask whether our models are complete. The universe seems to be telling us over and over again that there's more going on than we currently understand. Really violate the cosmological principle. Then we might need to rethink everything. Maybe the universe isn't as uniform as we thought. Maybe there are regions with completely different properties, different densities, different rates of structural formation. Maybe our models work for our local neighborhood but break down on the largest scales. This is genuinely exciting. I know it might sound scary, like the foundations of physics are crumbling, but scientists love this stuff. When observations don't match predictions, that's when the real discoveries happen. That's when we learn something new. Every time one of these impossible structures is found, it's an invitation to dig deeper, to come up with new theories, to test new ideas. And there's so much we still don't know. Dark matter, this mysterious substance that makes up about 27% of the universe, is still not directly detected. We know it's there because of its gravitational effects, but we don't know what it is. Dark energy, which makes up about 68% of the universe, and is causing the expansion to accelerate, is even more mysterious. We have no idea what it is, or why it behaves the way it does. These unknowns might be connected to the structures we've been discussing. Maybe the behavior of dark matter or dark energy on large scales is different than we thought. Maybe there are features of the early universe, things that happened in the first fractions of a second after the Big Bang that we haven't accounted for. The megastructures could be clues, hints pointing toward physics we haven't discovered yet. There's also the question of what we might be missing entirely. The South Pole wall was hidden behind our galaxy until just a few years ago. How many other structures are lurking in the zone of avoidance? How many are too faint for our current telescopes to detect? How many are so far away that their light hasn't reached us yet? The observable universe, the part we can see, is limited by the speed of light and the age of the cosmos. Light from objects more than about 46 billion light-years away hasn't had time to reach us. Beyond that horizon, there could be anything. More structures, bigger structures, completely different kinds of structures. And the universe beyond the observable horizon might be infinite. If it is, then there are infinite galaxies, infinite structures, infinite versions of everything we've seen. The scale is genuinely incomprehensible. Our entire observable universe, everything we've talked about in this video. This is why I find this topic so fascinating. It's humbling. We've made incredible progress in understanding the cosmos. We've mapped the cosmic microwave background with extraordinary precision. We've catalogued billions of galaxies. We've detected gravitational waves from colliding black holes. But despite all of this, we keep finding things that don't fit, things that remind us how much we still have to learn. The 10 structures I've described are just the tip of the iceberg. There are other anomalies, other mysteries, are the features of the universe that don't make sense yet. And there will be more discoveries in the future. New telescopes are coming online all the time. Future missions will probe even deeper, see even farther, find even more surprises. Each of these discoveries brings us closer to the truth, but it also reveals how far we have to go. The universe is not obligated to make sense to us. It just is what it is. And what it is, apparently, is far stranger and more complex than we ever imagined. So what should we make of all this? I think the honest answer is that we should stay curious and stay humble. The structures we've discussed are real. They've been observed and measured and studied by serious scientists using rigorous methods. But our understanding of them is incomplete. We have theories. We have hypotheses, but we don't have final answers. And maybe that's okay. Maybe that's even the point. Science isn't about having all the answers. It's about asking questions, making observations, testing ideas, and being willing to change your mind when the evidence demands it. They're saying, look, your models are good, but they're not complete. There's more out there than you've accounted for. Keep looking, keep learning, and that's what we'll do. Somewhere out there, someone might be on the verge of a breakthrough that explains everything we've talked about. Either way, the universe will keep surprising us. We're living in an age when we can look out at the cosmos and see things that humans have never seen before. We can map structures that span billions of light years. We can ask questions that our ancestors couldn't even imagine. That's a privilege. By the iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it came from space. You're literally made of stars stuff, looking up at the stars, trying to understand where you came from. They're part of the cosmic web that connects everything, the vast network of matter and energy that spans the observable universe and beyond. So the next time you look up at the night sky, remember that you're looking at something ancient and mysterious and beautiful, pushing the boundaries of human knowledge, one observation at a time. It's genuinely amazing to think that people from all over the planet, from all different time zones and cultures and backgrounds. I'll see you in the next one.